Okay, so today what we're doing is to continue. Last week we started with a little review of the signals and systems material. Today we are continuing that because we're doing a little bit of a review today, and it will be leading us now into the new material that we're going to start covering on spectrum analysis. All right, so today's topic is on the continuous time Fourier transform. And let's go forward. Right, so if you remember, in engineering, the idea of using frequency domain analysis is critical, especially in some disciplines like communications, for argument's sake. Those of you who are in that, you always talk about the bandwidth of channels that you're dealing with. And the bandwidth basically has to do with what is the range of frequencies that the particular channel can accommodate. And then we also use this in things like, for instance, speech recognition, where you use somebody, you're trying to identify voice. We use it all the time, for instance, with phones and other smart applications that respond to your, or are supposed to respond to your voice alone. And how it does that is by analyzing the content, the frequency content of the spoken word. And this is just a very short list of where you see it right now. Of course, well, we know it from way back when in things like your stereo equipment or the entertainment systems in homes and in cars and so on. You can adjust the frequency content to boost the low or the high notes, and as the case may be. The power systems, people do this a lot because harmonics represent a source of wasted energy. So if you have a system that is supposed to be a 60 hertz or 50 hertz system, but in the course of either generating that or using it, you are generating, like if it's a 60 hertz system and you're generating 120 hertz or 180 hertz on top of the 60 hertz, what you have is wasted energy there. Okay, so it's very critical in that regard. Something called load disaggregation, which is a nice signal processing application. This is where you take, for instance, you do a measurement of the power consumption, let's say on a house, and based on the signatures of the various components inside of that current, you can tell, well, okay, the air conditioner was used so much, the refrigerator used so much, and the pump used so much, and that kind of thing. So it's an important tool now, and especially maybe in our case now with utility rates probably going up, it might make sense to have a system that looks and see exactly what your energy use is being, what your money is being expended on, and try to reduce that if possible. Stock market, I mentioned that before, that they started to use signal processing analysis in that, which is really frequency domain, to see how things vary over time. Audiology, hearing loss, hearing impairment, making devices that can enhance the hearing capacity of people, image processing, and so on. So all of these things use frequency domain analysis. All right. Of course, if you now, because I'm watching you on a screen here, as I mentioned some time ago too, if you need to catch my attention, you're going to have to say something. All right. If you're not hearing me or you can't see what I'm doing, let me know, but you have to try and drag my attention. If there's a question and you want to ask it, okay, if you put something in the chat, you need to tell me, hey, something is in the chat, so I'll check it, because I have a full screen here and I'm not seeing the chat, okay? Right, so if you recall, when we spoke about the frequency content of a signal, we call that its spectrum. And the term really came back from the old what do you call it, physics situation where you took light, you pass it through a glass block, and you had this splitting up of the colors that they call the spectrum, and that was just extended all the way through. So anytime you're doing harmonic or frequency analysis, the information that you get out is the spectrum. And how you go about doing that is by something called spectrum analysis. For continuous time signals, you can use a device called a spectrum analyzer. And here's a picture of one. We actually have a couple of them in the labs downstairs. They are incredibly expensive devices because if you're using continuous time signals, it is using analog electronics in the most what do you call it? The most prominent form is using analog electronics to do the filtering. And what it does, it takes a signal coming in, it passes through it a series of filters that you can adjust the bandwidth and the center frequency and so on. And then it displays the amplitude coming out in continuous time on a screen. Of course, now the line is blurring between doing that in real time and doing that with digital signal processing because of how fast both analog and digital systems now can operate so incredibly fast, but the discrete signal processing allows you to do so much more that the line is now blurring between that kind of device that you have in front of you there and the more common one, which would be even using just a laptop, a box that you hook up to the laptop and is doing the analysis, the data acquisition for you, but everything else is being done by software. All right, but how you do it is using something called a spectrum analyzer now. So leading into that, we had that sort of conversation, and we said that if you take any periodic signal now, that what you can do is to express the periodic signal as an infinite sum of something called orthogonal functions. That's just a fancy math word. Basically, what it means is that you can take any periodic signal, and the orthogonal functions are two functions where if you do something called a cross product, the answer is 0. Sine and cosine are such. And in the particular case of using sine and cosine, that is something that we call the Fourier series. And it came up because of the French mathematician Joseph Fourier. So that what happens is that each signal, once it is periodic, you could express it as a sum of sinusoids and cosine sinusoids that are multiples of the fundamental frequency. And you spent a lot of time, we did some of that in signals and systems, and you did some of that in the ECNG 2013 math course as well. The idea behind it, and this is what I always like to have people do, is that if you're doing something mathematically, there must be a sort of a physical interpretation, if you like, for it to help you to understand. So what you have, for instance, and we saw is that this is a square wave. The line hasn't printed too well, right? So you have a square wave or a rectangular wave, and then what you could see is that this now you can express according to this Fourier series. You can express it in terms of a DC, which is 0 frequency, the fundamental, right? The first harmonic and the second harmonic. All right. And if you were to take these individual signals now, these for the DC and the other harmonics, and you add them back up, what you get is that the first 4 terms is starting to give you that signal, and the more you add is the closer it will come, of course, to the original square wave. The problem, of course, is that in order to fully represent this, we need an infinite number of these. All right, but if you were to go to infinity, that you would be able to go from the time domain into this domain, which is showing you the frequency information, basically. Right? And you spend time doing that. There was some manipulation, and I know some people still have a little bit of difficulties with it. The main issue with the Fourier series is that most of it is just some calculus. Okay, once you understand what it is about, then the other part of it is actually doing the trigonometric what do you call it, integral, and it's long. Depending on what you're dealing with, you have to integrate by parts, and sometimes you have to integrate by parts several times to get the answer. So that what was done is that we look for shortcuts. So, you know, periodic signals of a particular type, you say, okay, we'll only have sine components, and periodic signals of a particular type might only have cosine components. And then the whole thing about odd and even signals having, you know, particular either sine or cosine components there to shorten the manipulation. But I think if you understand what it is trying to do, then the rest is just really tedious calculus and algebra. All right, which is where maybe people got fell down a little bit in it. For our purposes, there are two versions of the Fourier series. The one that gives you, you know, that it is a that the signal is a sum constant plus a sum of sines plus a sum of cosines. And what we did in our use of it, because we were more interested in going forward with how to use that in signals and systems, is that we recognize that there's a relationship between the complex exponential E and sine and cosine that we call Euler's relationship. So we were able to go from this form, which is what we call the trigonometric form of the Fourier series to something called the complex exponential form, which looks like this, which is quite compact. And the good thing about it is that it reminds you of the Laplace transform. So we had the analysis. You remember, if you recall, this one here was the analysis equation, and the other one was the synthesis equation. And the important thing in all of this was these coefficients, because the coefficients gave us the values of each of the sines and cosines that made up the original signal. Yeah, I'm hoping that at least you recall some of that, right? So that the complex exponential form here is a sine and a cosine, but because E is related to sine and cosine, now we remove that, and we have everything expressed in terms of E. And then the individual weights inside of here, which are the actual components that make up the whatever signal it is you're analyzing, has a form that looks like this. And this is very close to the Laplace transform look, right? It's the integral of something by a e to the something as well, e to some negative power, right? So it's fairly easy to remember, right? So hopefully you would recall some of that. And this was the parts that we call the complex Fourier coefficients. K equal to naught, in other words, C naught was the DC component. K equal to 1, or in theory, plus or minus 1, if you like, right? Was the first harmonic component. K equal to 2, or the fundamental. And then K equal to 2 was the first harmonic. K equal to 3 was the second harmonic, and so on, right? And if you remember briefly, those of you who do music, there's a little difference here in that I think musicians call K equal to 1, they would call that the first harmonic, and K equal to 2 the second harmonic, and so on. So there's a little, depending on what you're dealing with. So what we call the fundamental, sometimes musicians call it the first harmonic, okay? I'm hoping that you're recalling that. Are you? Let me know, eh? You remember that vaguely? Yes, no? Anybody? Perhaps? Okay. perhaps. Okay. So because the coefficients are complex numbers, you remember any complex number you can express with a magnitude and an argument. Okay. In our case, the magnitude of CK is what if we plot CK, the magnitude of this coefficient, then we got something called the amplitude spectrum of the particular signal. And if we plotted the argument of CK, we call that the phase. So the angle of this is the phase spectrum. And you remember, one of the things is that we are very careful in that all signals have both an amplitude and a phase. The amplitude relationship is nice. It tells you all of the components that make up the signal. But the phase is very important because it tells you the timing relationship between each of them. Okay, if something is 180 degrees out of phase, two identical signals will cancel. If they are in phase, they reinforce and you get twice the amplitude. So the phase relationship between signal components and spectral components is important. And that is what makes a signal unique, right? So your voice or my voice would be because not only of the amplitude spectrum information, but because of this specific phase information. So both parts are required to give you some a complete picture of what it is. And then importantly, the Fourier series, the answers that you get are integer multiples of the fundamental. So K is an integer. All right, so a continuous time periodic signal, when you do the spectrum has discrete components. And the discrete components occur at multiples of their fundamental frequency. All right, so that's an important thing. And we saw it here. We took, this was a rectangular wave. The period of the wave was T, and the actual duty cycle was determined by the pulse width here. And if you apply the complex exponential form, you got that the coefficients was this sine x over x. Sine x over x, or something that we call a sinc function. Right, you may have met that. Well, you met it. We did it in signals, but I'm sure you have met it already or since then in communications. Right, so it's a sine x over x function, and if you plot it, this is what the magnitude of the function looks like. The actual function, if you plot it, is like this, and it goes on forever. All right, so the magnitude of the function looks like this. And then what you notice is that each of the lines here represents a value of K. So right here, the middle, this is K equal to 0. This one will be K equal to 1. This is also K equal to 1 here, right? Why you have both negative and positive is because, of course, you're dealing with complex conjugates. So you would have both positive and negative values, but the imaginary components cancel in the end. So it all turns out all right. But, and then K equal to 2 is here and so on. So for this kind of waveform, the spectrum, notice this is continuous time. So this is continuous time. Notice that this spectrum is discrete. And the spectrum only has values at these points. All right. So if you do it, and you look at the, once you do the derivation and you get the values for CK, you can see that the line spacing, so that is between this line and this line, that line spacing is pi a over t apart. Now notice what a is, A is the width of the pulse, T is the period. Right? So if the spacing is pi, where are we? The spacing is pi A over T apart. So you can see already if A gets bigger, as A gets bigger, the spacing increases. As T gets bigger, the spacing decreases. Everybody seeing that? Make sense? All right, good. There we go. See, it's a good thing to have your coffee on hand so you can have it at home. There you go. So as A increases, the spacing between these lines gets bigger. And as T increases, the spacing gets smaller. The other thing is these points here, the zero crossing points. The zero crossing points occur at multiples of the points where this particular bit is zero. So if you look at it, wherever K pi A over T is equal to some multiple of pi, if this inside of here is some multiple of pi, it means the sign of that is going to be zero. And if you look at that, that means at some interval where K is equal to some integer M pi over MT, sorry, MT over A, which is this. Yeah? So look at what happens here. If I make A bigger, if A is bigger, so in other words, the duty cycle of the square wave or of the rectangular wave increases. So as I make the duty cycle bigger, according to what I have here, if A goes up, these lines start to move further and further apart. Yeah? And the zero crossing points, if A gets bigger, what happens to the zero crossing points? Remember, the zero crossing points is MT over A. So if A gets bigger, the lines move further apart. But what happens to the zero crossing points? The zero crossing points start to move closer together. All right, so this is the first zero crossing point. So as A goes up, these spaces get bigger, but this space here, the zero crossing points, start to squish together. Okay, so that's the sort of thing that you're looking at. Also, if the period T increases, so in other words, if instead of this, let me just clear some of this here a little bit. If the period increases, so instead of this, if I have this now, right? So this is still A, but the period is now increasing. If I increase the period, according to this, the line spacing, which is pi A over T, starts to get smaller and smaller. So as I increase the period now, we're starting to get everything crunching up a little bit more. And then if I increase the period, which is T, the zero crossing point, right? The zero crossing point, which is related to T. So as T gets bigger, the zero crossing point starts to go this way. So everybody seeing that little manipulation there? Yeah, no, maybe. Right? So again, this was kind of like what we were talking about. So you have a signal here. You have a square wave. The square wave Continuous time has a discrete time spectrum. It only exists at these points. If I make this square wave where the width, the duty cycle of the square wave gets smaller, then if the duty cycle gets smaller, the lines here start to move closer and closer together. If I make the period bigger, the lines, the zero crossing line starts to move further and further away. Remember that when we talk, because we'll be coming to some signals a little bit later on, and you'll see what that manipulation means, right? So the important thing here, a periodic signal has a discrete spectrum, all right? And if ever you come across that again, and you're trying to remember, wait, a periodic signal, what kind of spectrum it has? Think of a single sinusoid. How much frequency component does a single sinusoid have? One. So a continuous time sinusoid has one frequency component. In other words, one discrete value. So all periodic continuous time signals have discrete spectra, right? And this is what we are saying. What happens as the period increases? As the period increases, which is this here, as t increases, the line spacings get closer and closer together, and the zero crossing spectrum moves further and further apart. And if you remember, anybody remembers what was the spectrum of an impulse? A unit impulse. What was the spectrum of the unit impulse? Anybody remembers? No, the spectrum. What was the frequency content of a unit impulse? If you did it, you would remember that the frequency content was a flat, right? The spectrum of the impulse, delta omega, if you want, was a continuous flat line. Infinite amplitude is 1, and this is omega. All the frequency components in them are continuous flat line at 1 all the way through, which is why we said the unit impulse was such a powerful signal, in that once you imposed it, that you're imposing an infinite number of frequencies on a system. Of course, it's impossible to get this, but you could see how we could, if I take my square wave, my square wave is giving me this. If I start to make the period get bigger and bigger, so it's starting to look like this. As I stretch out the period, these points, the zero crossing points, start to move this way. So the spectrum starts to flatten out. And then if I make this smaller, so that I'm trying to get as close to an ideal impulse as possible, then the individual points start to move closer and closer together. So in the ideal case, eventually this flattens out and you end up having this flat continuous spectrum. All right, so that was it, the sort of the interpretation of what we had going forward. Yeah, anybody recall that? Yeah, go back and check some of the slides on that, because that interpretation was important for us. Okay, so some of the things that of course, with the Fourier series, there are some limits. It applies to periodic signals. So what happens now if we have to deal with something, a non-periodic thing, something like speech, or a single word that is spoken, but it never repeats itself? How do you handle that? And to answer that, we said, well, what was the period of a non-periodic waveform? And we took a very engineering approach to it. Remember, in engineers, you have to in engineering, you have to think a little bit sideways sometimes. So a non-periodic signal, right, is we decided to treat it as a signal where the period was infinite. So in other words, our engineering approach was to say, okay, really and truly, everything is periodic, but the non-periodic signal, the period is so huge that it doesn't repeat itself. All right, so we say, okay, we will take a non-periodic signal as one where t is almost infinity. And if we do that, what we were able to do now is to make some adjustments to that Fourier series that we had. So if t is going to infinity, remember omega naught, the fundamental omega naught is 1 over t. So if t goes to infinity, omega 0 tends to get to something very small. K omega 0, remember, as we're going to infinity now, the spacing in the spectrum starts to move into each other, and eventually it becomes continuous. And what we had was that we moved from this part, these are the coefficients of the Fourier series, to something looking like this. Right? If you remember, we did the manipulation here, and I'm not asking you to derive it, but just to see how we evolved. We started with the Fourier series, and we evolved to this thing now. And the harmonic, because now we have, as we saw, if k starts to get, sorry, if t starts to get big, the number of k's, the individual components, gets so large that eventually k is now continuous. And so that the spectrum now has become a continuous variable. T is infinite, so that we could move the limit of integration from over the period, which is what you would do for the Fourier series now, to over all time. So we now got on to this point, and then we made a little bit of we juggled around a little bit to get rid of the delta over 2 pi. And then I'll come back to this. With a little bit of juggling, we got this here. Right? So we combine, what we said is that basically, if we define C omega multiplied by 2 pi over delta omega, we redefine all of this. We call this now X omega. Right? So this was a definition here. We defined that little thing as X omega. We got this into a form looking like this. And this was what we call the continuous time Fourier transform of a signal. So a non-periodic signal, right? Remember, xt is non-periodic, right? The Fourier transform of that was, or the continuous time Fourier transform, to be correct, was now given by this expression here. And then let me just go back to this slide before. Just to make the point that a periodic signal has a discrete spectrum. We saw that from the square wave. The non-periodic signal has a continuous spectrum. Right? So we go back here. And well, in our case, we were just calling this the Fourier transform, but I kept pointing out that the more correct version was something called the continuous time Fourier transform. And that's important for us to remember, because we're going to do on Wednesday, we're going to start doing something called a discrete time Fourier transform, which is a modification of this, because we're dealing into some mechanism that we could do this automatically. I can't do this. I can't ask a computer to do this, right? If xt is non-periodic, so let's say I have this, right? So this is a simple pulse. That is fair enough. But how do I accomplish this? There's no way I could program any piece of hardware or software, sorry, to do that sort of manipulation. So this is still something that has to be done on paper. Sit down and you do the calculus. The other part about this is that this resembled our Laplace transform, right? If you remember, the Laplace transform is xt e to the minus st dt, right? Of course, the Laplace transform integrates from 0, well, actually a little before 0, up to infinity. But for if you looked at the two of them, the actual integral itself is identical, except for the fact that S here and j omega up here. And we'll talk about that relationship between S and j omega as we go through this. All right. And of course, if you, as we mentioned, there's no use having a transform unless you have an inverse transform. Transforms are designed to take you from one space to another, right? But it can't be a one-way ticket, otherwise the transform is useless. So if you have to go from time to frequency, you must have a way of getting from frequency back to time. And this was the inverse Fourier transform here. And we took the 2 pi. 2 pi is just a constant, right? We have it on the inverse part. We did that because in order to have the forward transform and the Laplace transform look the same. All right. So the Fourier transform allows us to go from the time domain to the frequency, and the inverse transform allows you to go from the frequency domain back to the time. The two of them are known as, of course, the Fourier transform pair, because all transforms have to have a forward and a reverse part of it. And they apply, most importantly, they apply to non-periodic signals. Right? The Fourier transform, the transform applies to non-periodic signal. We started off by saying the Fourier series applies to periodic signal, and we went. So we've started a little bit of an evolution here. So we have a continuous time signal, right? We have the Fourier series, right? And then if the period of the signal starts to go to infinity, we go from here to the Fourier transform. Right? And and in fact, the correct version of this is the continuous time Fourier transform. Okay, and then after this, now we're going to look and see, well, how to go forward here. So we've started this sort of evolution, if you like. And then, of course, we have standard notations for them that the Fourier transform of a signal is either x omega or xj omega, all right? And sort of standard notation, you would see it in the textbooks and so on, that they, just like they have a cursive L for the Laplace transform of a signal, of course, the Fourier transform uses a sort of cursive F for it, okay? The similarity in form, many of the properties are similar, right? And there were some important exceptions that we dealt with. We're not going to go back with them here, but just remember that the form of the transform is similar. So if you were looking to get the continuous time Fourier transform of something, then, and you can't remember how the answer looked like, you could probably look at the Laplace transform for the same thing and then say, okay, right, the form is like that. And if I replace S with j omega, I will get an answer that is generally close to where the answer is, but you have to be careful that there are some exceptions dealing with that. All right? So, questions. This was like a condensed review of some of the stuff that we did. So let me hear questions. None? At least when I'm seeing you face to face, I can know if people dozing off or if they're still here. So, all right, good to go. All right. But again, if you have forgotten some of this stuff, what we did in signals and systems when we spoke about the moving from the Fourier series to the Fourier transform, that is the important part. Okay, I'm not going back over the Fourier series, and you're not going to get Fourier series stuff inside of here. What I just needed for you to understand is that you start off with a continuous time signal that is periodic, right? And then you go to a continuous time signal that is non-periodic, and that leads us now to the continuous time Fourier transform. We're starting to get there, but we can't, in signal processing applications, we can't use this. But this is a start. And what we're going to talk about Wednesday now is two things. We're going to talk formally about sampling. And then when we apply sampling to the continuous time Fourier transform, we're going to get now a new transform called the discrete time Fourier transform, which is starting to move us into a direction that you can actually compute this thing numerically. You don't have to sit down with pen and paper and do integration. All right? Okay, so again, everybody all right with that? Make some sense? As I say, hopefully it should you should recall some of this thing from somewhere. All right. Okay, so I will have let me stop the recording here. As soon as it's available, I'll put it up now, trying to